Hi, welcome. Suppose you're trying to calculate the limit of a fraction and that you run into the problem that both the numerator and the denominator go to zero. What to do? Is this a deadlock? Not really. More than 300 years ago, a method was developed to deal with such a situation. It is known as L'Hopital's rule and based on taking derivatives, as will be shown in this video. Let's first revisit the limit concept by considering an easy example. Here we have a function which is composed as the quotient of two functions. If x goes to 1, then the numerator approaches 2, while the denominator approaches 3. This leads to the result 2 over 3. In general, such limits are thus easily determined whenever the limit of the denominator is not equal to 0. In the case that the limit in the denominator is equal to 0, the situation is a bit more complicated. In the example on the slide, the numerator approaches 2 as x goes to 1, while the denominator approaches 0 from the right as x goes to 1. It can thus be concluded that the limit does not exist and that the fraction becomes infinite as x approaches 1. It may also happen that both the numerator and the denominator approach 0. In such a case, the limit is said to be of an indeterminate form. Its value is not obvious. In some cases, as in the example on the slide, the limit can still be determined by simple techniques such as cancelling common factors. Note that the factor x minus 1 is present in both the numerator and the denominator, and it is close to 0, but not equal to 0 as x approaches 1. So, by dividing the numerator and denominator by x minus 1, we easily find that the limit equals 2. However, such simplifications are not always possible. What to do with the limit presented on the slide? Both the numerator and the denominator approach 0 as x goes to 1. So we have again a 0 divided by 0 situation. However, the cancellation technique from the previous example does not apply here, and there seems to be no easy way out. Still, let's attempt to evaluate the limit by looking at some graphs. The green curve represents the numerator, the natural logarithm of x. The blue curve, the denominator, 1 minus the square root of x, and the orange curve, the division of the two. Note that the orange curve has a hole at x is 1, since the fraction is of the 0 divided by 0 type and does not exist there. The curve suggests that the limit is minus 2. Having a closer look at the area near x is 1, observe that the green and blue curves are almost straight lines. In other words, we can say that the functions are well represented by their linear approximations at x is 1. Note that the numerator has slope 1 and that the denominator has slope minus 1/2. We can conclude that near x is 1, the ratio between log of x and 1 minus square root of x is close to 1 divided by minus 1/2. This is indeed equal to minus 2. The general rule says that if the limits of both the numerator and the denominator are equal to 0 as x approaches a certain value a, the limit of the fraction is equal to the limit of the quotient obtained by replacing the numerator and the denominator by the derivatives. So in the example, we replace log x by its derivative 1 over x and 1 minus square root of x by its derivative minus 1 divided by 2 times the square root of x. Now we no longer have a 0 divided by 0 situation, and we easily find the limit by substituting the value 1 for x, leading to the limit minus 2. The rule has been named after the French mathematician Marquis de L'Hopital. There's a lot of confusion on how to spell his name. An even more confusing issue is that he did not discover the rule himself. This was actually done by the Swiss mathematician Johann Bernoulli in 1694. Marquis de L'Hopital had bought the rights to Bernoulli's scientific results. The rule was published in a book authored by L'Hopital that appeared in 1696, 2 years after Bernoulli's discovery. We can conclude that L'Hopital's rule is a very useful tool to evaluate limits of the 0 divided by 0 type. It can also be applied to limits of some other types, a nice area to be further explored. Good luck!